This passage is adapted from John Chambers and Jacqueline Mitten from Dust to Life, the Origin and Evolution of Our Solar System. Differentiated asteroids are made up of layers of different materials such as iron ore, a rocky mantle, and a thin volcanic crust. Primitive asteroids are undifferentiated asteroids that are thought to have changed little since they formed. Scientists believe that iron meteorites come from the cores of asteroids that melted. But what happened to the corresponding rocky material that formed the mantles of these bodies? A few asteroids have spectra, characteristic wavelengths of light that asteroids reflect. A few asteroids have spectra that match those of mantle rocks, but they are very rare. Some non-metallic meteorites come from asteroids that have partially or wholly melted, but these do not match the minerals we would expect to see in the missing mantles of the iron parent bodies. These exotic meteorites must come from some other kind of parent body instead. Okay, so here we are saying that scientists believe that iron meteorites come from the cores of asteroids that melted. What happened? The question is, what happened to the corresponding rocky material that formed the mantle of these bodies? A few asteroids have spectra, which I think is the plural of spectrum, that match those of mantle rocks, but they are very rare. Some non-metallic meteorites come from asteroids that have partially or wholly melted, but these do not match the minerals we would expect to see in the missing mantles of the iron parent bodies. Okay. The rarity of mantle rocks in our meteorite collection and in the asteroid belt, known as the missing mantle problem, is a long-standing puzzle. There are several reasons why iron fragments might survive better than rocky fragments when asteroids break apart. Iron lies in the core of a differentiated asteroid, while rocky material lies near the surface. Thus, rocky material will be the first to be removed when an asteroid is bombarded, while iron is the last to be exposed. As a result, rocky fragments have to survive in space for longer than iron ones. Most of the rocky mantle may be peeled away in small fragments, chips from the surface, while the iron core remains as a single piece, making it harder to disrupt later. Last and most important, iron is much stronger than rock. A piece of iron is likely to survive in the asteroid belt at least 10 times longer than a rocky fragment of the same size. So this paragraph basically tells you why iron is likely to survive at a higher rate compared to the rocky surface of an asteroid, because one, iron is at the core of a differentiated asteroid while rocky material is at the surface. Second, most of the rocky material is peeled away in small fragments while the iron core remains as a single piece. And third, iron is more stronger than rock. If most differentiated bodies broke apart early in the solar system, perhaps all the mantle material has been ground down to dust and lost over the billions of years since then. This would mean that intact differentiated asteroids are very rare in the asteroid belt today. Perhaps Vesta, a differentiated asteroid with a diameter of more than 300 miles, and a handful of others are all that remain. However, collisional erosion cannot be the whole story. Primitive asteroids, the parent bodies of chondritic meteorites, the most common type of meteorite found on Earth, are no stronger than the mantle rocks from differentiated asteroids. How did so many primitive asteroids survive and almost none of the differentiated ones did? Part of the explanation may simply be that differentiated bodies were relatively rare to begin with and none have survived. Still, if almost all differentiated bodies were destroyed in violent collisions, how did Vesta survive with only a single large crater on its surface? So here the question is about the difference between primitive asteroids and differentiated asteroids, right? Remember that the differentiated asteroids are made up of layers of different materials such as iron ore, a rocky mantle, and a thin volcanic crust, right? So the question is that there is no difference per se between primitive asteroids and differentiated asteroids. Primitive asteroids are no stronger than differentiated asteroids. Then how did so many primitive asteroids survive? Then the question can be answered with the reason that perhaps differentiated bodies were relatively rare to begin with, and so they have not survived. But then, how do you explain the existence of Vesta with only a single crater on its surface? Astronomer William Botke and his colleagues recently came up with a possible explanation. Perhaps the parent bodies of the iron meteorites formed closer to the Sun in the region that now contains the terrestrial planets. Objects would have been more tightly packed nearer the Sun, so collisions would have been more frequent than in the asteroid belt. Many, perhaps most differentiated bodies were disrupted by violent collisions. Gravitational perturbations from larger bodies scattered some of these fragments into the asteroid belt. Both iron and rocky fragments arrived at the asteroid belt, but only the stronger iron objects have survived for the age of the solar system. Later on, the parent bodies of primitive meteorites formed in the asteroid belt. Most of these objects survived, leaving an asteroid belt today that is a mixture of intact primitive bodies and fragments of iron. Okay, so how has William Botke explained that sort of contradiction um, in terms of a very low number of differentiated asteroids? He says that it's possible that the parent bodies of these iron meteorites, they formed closer to the sun, right? As against the primitive asteroids which formed in the asteroid belt. And because they were more tightly packed near the sun, they would have had more collisions. And so more differentiated bodies were disrupted by violent collisions. And so most of them were destroyed, and only a few survived to appear or to come to the asteroid belt. Right? So that's the explanation that Botke comes with. The main purpose of the passage is to discuss a study intended to explain the high number of meteorites on Earth that have come from primitive asteroids, describe competing hypotheses about the conditions in which primitive asteroids initially formed, present a scientific debate about the prevalence of differentiated asteroids in the asteroid belt in the early solar system, account for the scarcity of a component of differentiated asteroids in the asteroid belt and among meteorites on Earth. Okay. So obviously we can eliminate A and B because A and B are focusing on primitive asteroids, while the focus of the passage is on differentiated asteroids. Now, if you look at C, it says present a scientific debate about the prevalence of differentiated asteroids in the asteroid belt in the early solar system. So is that correct? I mean, are we only talking about the early solar system? Because we are actually talking about the presence of differentiated asteroids in the solar system today, right? We are also talking about a body like Vesta and how come this survived while other differentiated asteroids, this did not. So I don't think early solar system is the focus here. Account for the scarcity of a component of differentiated asteroids in the asteroid belt and among meteorites on Earth. Okay, so this looks like a good answer because we do discuss the fact that there was a scarcity of differentiated asteroids in the asteroid belt and among meteorites, and the passage is concerned with why that could be. So I like D. As used in line 25, disrupt most nearly means while the iron ore remains as a single piece, making it harder to disrupt later, right? So that is making it harder to fracture later, because we are basically talking about how the rocky surface gets kind of broken up into smaller pieces, but the core does not. So we are looking at disrupt to mean something that breaks down. So none of these have the connotation of breakdown. So A. The passage more strongly suggests that if collisional erosion within the asteroid belt was sufficient to explain the situation discussed in the passage, then as a result, scientists would expect to find that Vesta is not the only large differentiated asteroid in the asteroid belt. The asteroid belt has far fewer primitive asteroids than it currently does. Iron fragments in the asteroid belt tend to be smaller than rocky fragments in the asteroid belt. There were originally about as many primitive asteroids as differentiated asteroids in the asteroid belt. Okay, let's work with the line numbers 35, 37, 38, 39. 35, 37, 38, 39. 39, 44, 44, 47. 39, 44, and 44 to 47. And we are looking for evidence for what exactly? We're looking for evidence for if collisional erosion within the asteroid belt was sufficient to explain the situation, what would scientists expect to find? Okay, perhaps Vesta, a differentiated asteroid with a diameter, and a handful of others are all that remain. Okay, so this doesn't explain that. However, collisional erosion cannot be the whole story. Primitive asteroids, the parent bodies of chondritic meteorites, the most common type of meteorite, are no stronger than the mantle rocks from differentiated asteroids. How did so many primitive asteroids survive when almost none of the differentiated ones did? Part of the explanation may simply be that differentiated bodies were relatively rare to begin with. So it's C, right? It's C because if collisional erosion was the main, yeah, so if collisional erosion was sufficient to explain the situation, then it would mean that the number of primitive and differentiated asteroids would be the same, right? Which is what D is saying, because there is no other reason to explain the difference in their number, because primitive asteroids are no stronger than differentiated asteroids. Okay, the question in lines 47 to 49 mainly serves to 47 to 49. Still, if almost all differentiated bodies were destroyed in violent collisions, how did Vesta survive with only a single crater? So this brings the other part of that argument, that if collisional erosion was not responsible the for the outcome that we see today, that is the large difference between the number of primitive and differentiated asteroids, then what explains the presence of Vesta, right? Which does not show evidence of collisional fracture. Highlight an anomaly that challenges an idea presented earlier in the passage. Present a hypothesis tested by scientists who are introduced later in the passage. Cast doubt on the likelihood that the central problem discussed in the passage will be resolved. Point out the lack of observational data concerning a particular asteroid discussed in the passage. So this is A, because what Vesta does is that it kind of shows that this argument of collisional erosion that the passage forwards may not be a complete picture, because Vesta did survive as a differentiated asteroid. It did survive this entire time, and it is an anomaly because it doesn't explain the whole process of why differentiated asteroids have not survived. This is not a hypothesis that is tested. It is not casting doubt on the likelihood of the problem getting resolved. And this is not about the lack of observational data. As used in lines 53 to 54, contains most nearly means perhaps the parent bodies of the iron meteorites formed closer to the sun in the region that now contains the terrestrial planets. That now encompasses, right? To encompass is to have, right? So that region has the terrestrial planets. So that's the best answer. Restrain doesn't fit the context, embody doesn't fit the context, and neither does control. According to the passage, Botke and his colleagues explained the presence of iron fragments in the asteroid belt by asserting that the fragments were. Okay, so what was Botke saying again? Botke came up with a possible explanation. Perhaps the parent bodies formed closer to the sun. Objects would have been more tightly packed, so collision would have been more frequent. And most differentiated bodies were therefore disrupted by violent collisions. Okay, so that was Botke's explanation. So he explains the presence of iron fragments by asserting that the fragments were remnants of differentiated asteroids that were destroyed in collisions in the asteroid belt. No, not in the asteroid belt. Created relatively close to the sun and ended up in the asteroid belt due to the gravity of large objects. Formed on terrestrial planets and ejected into the asteroid belt by collisions with primitive asteroids. Formed in the region of the terrestrial planets but knocked into the asteroid belt by collisions with the parent bodies of primitive asteroids. Okay, so definitely not C. We know that they were formed close to the sun, but we are talking about gravity of large objects, right? Um, yeah, it is gravitational pull that brought them here, not the collisions with the parent bodies of primitive. It's very clearly given that gravitational pull was responsible for them ending up in the asteroid belt. Data in the table best support the conclusion that the majority of the mass in the asteroid belt as a whole is in asteroids that are primitive, basaltic, high in reflectivity, low in reflectivity. Okay, the majority of mass, right? Okay, portion of the belt's total mass. It's this, right? All objects in the belt, but the four largest. Okay, so majority of the mass comes from here. So it is, yeah, these are primitive asteroids, right? They are possibly parents of chondritic meteorites. Yeah, so primitive. Assuming that the four largest asteroid belt objects are among the 11 listed asteroid types, which statement about these asteroids is best supported by data in the table? Okay. None of them is type V, none of them contains carbon, one of them is type K, two of them are the same type. The four largest asteroid belts are among the, okay. So, four largest, okay. Oh, so we have to look at the differences between these numbers, right? So, for example, not consider this, not consider this. So, where there is a difference, we only consider those, right? So, there is this, there is this, and there is this. These are the only ones where there is a difference. So, contain carbon, low reflectivity, contain carbon, primitive, and mainly Vesta and related asteroids, basaltic. Okay, so, so what are we looking at? We are saying which statement about those asteroids? None of them is type V. What is type V and type K? Oh, right. Okay, these are the types. So none of them is type V. One of them will have to be. So A is wrong. What about type K? Yeah, type K is also not. So that, which is that option about type K? Yeah, none of them is likely to contain carbon. Two of them are the same type. Yeah, two of them have to be the same type because we only have three, right? And we are talking about four categories. So two of them have to be of the same type. Yeah. Taken together, the passage and the table most strongly suggest that the model proposed by some astronomers would imply which conclusion about type C asteroids? Okay, let me first look at type C asteroids. Type C is this. They contain carbon, possibly parents of chondritic meteorites, and they are primitive. Okay, so what is that? They come from type S asteroids that melted. They once comprised a smaller portion of the asteroid belt than type V asteroids did. They have experienced fewer collisions than have type L asteroids. They are younger than type M asteroids. Okay, S, V, L, and M. Let me just look at S, V, L, and M. S, V, L, and M. Okay. So similar to some chondritic meteorites, maybe primitive, contains silicates and iron, possibly parents of some chondritic meteorites, mainly Vestine-related asteroids. Okay. Moderate reflectivity possibly represent the metallic cores of formally differentiated bodies. So I'm going to eliminate L and S option because they are similar to what C is saying. So let me just go back to the question. L. Okay, they once comprised a smaller portion of the asteroid belt than type V asteroids did, and they are younger than our type M asteroids. Okay, so type V, mainly Vestine related asteroids. So on the face of it, I'm interested in the type V option because we talk about Vesta in the passage. So let me just look at that again. They once comprised a smaller portion of the asteroid belt than type V asteroids did. A smaller portion of the asteroid belt. Okay, let's work with the line numbers 1 to 2, 17 to 18. 1 to 2, 17 to 18. Okay. 30, 35, 60, 64. 30 to 35, 60 to 64. Okay, let's see this. Scientists believe that iron meteorites come from the cores of asteroids that melted. Okay. Iron lies in the core of a differentiated asteroid, while rocky material lies near the surface. If most differentiated bodies broke apart early in the solar system, perhaps all the mantle material has been ground down to dust and lost over the billions of years. This would mean that intact, differentiated asteroids are very rare in the asteroid belt today. Okay. And both iron and rocky fragments arrived in the asteroid belt, but only the stronger iron objects have survived for the age of the solar system. Later on, the parent bodies of primitive meteorites formed in the asteroid belt. Okay. I see that there is a very clear explanation of age, that the differentiated bodies are older than the primitive asteroids, right? Because they both arrived in the asteroid belt, but only the stronger ones have survived in the age. And then the parent bodies of primitive meteorites formed, right? So I'm definitely looking at the option that talks about age now. They are younger than type M asteroids. Okay, type C asteroids are possibly in type M. Yeah, so I will definitely go with D now because there is a component of age in this. Now the question is, which is the right option for that? Because if you're looking at yeah, I think I'll go with D because that's where we are talking about survived into the age of the solar system. And then the primitive bodies were formed. So I'll go with D for this one.